M. Victor Anthony Raj. He has pursued his bachelor's, master's and MPhil in physics. He then went on to pursue his PhD in physics at the University of Madras as well. He then went on to work as a lecturer at Thiruvalluvar Arts and Science College and Idya Engineering College for Women. Since the year 2006, he works as the lecturer and assistant professor at Loyola College, Chennai. With regard to research, he has published several papers in international journals, namely Radio Wave Propagation over Salem, Linear and Non-Linear Optical Properties of Pure and Doped Selenium Malate Single Crystals, and many more. He has also attended several conferences and seminars, namely International Conference on Materials Science and Technology, National Conference on Higher Education at Crossroads held at Loyola College, National Seminar on Crystal Growth 12 held at VIT University, and many more.
Welcome to UGC lecture series BSc Physics Honours Semester 6 Statistical Physics Lecture 1. In this lecture, we are going to see the concepts of entropy and thermodynamic probability, Maxwell's Boltzmann distribution law, ensemble, then summary about all these concepts. Entropy. The concept of entropy was first introduced by Clausius in the year 1854 while working on the formulation and application of the second law of thermodynamics. Second law of thermodynamics is an important concept in heat and thermodynamics. There, entropy of a system is understood. Entropy of a system is a measure of disorder of its molecular motion. For example, if there is a gas in a container, the gas molecules will move all around the container. Then the motion of the gas molecules will be random in manner. These gas molecules' motion will be disturbed when heat energy is supplied. Here, entropy is related to disorder of the molecular motion of a system. Imagine a gas system. Greater is the disorder of molecular motion of a gas system, greater is the entropy. So, entropy means a measure of disorder of a system. Example for the entropy is, if heat is supplied to the system, the disorder of the molecular motion increases, therefore, entropy increases. That means, to a gas molecule system, when heat energy is supplied, gas molecules will obtain the supplied heat energy and will move here and there randomly very fastly. So, disorder will be more, therefore, entropy increases. This is what said as, if heat is supplied to the system, the disorder of the molecular motion increases, thereby entropy increases. And if heat is extracted from a system, the disorder of molecular motion decreases. The meaning of the extraction of heat from a system. To extract heat from a thermodynamical system, we must bring the thermodynamical system in contact with lower temperature thermodynamical system. So, automatically heat transfer will take place. Heat will flow from hotter body to colder body. So, hotter body will lose some heat energy. This is how heat is extracted from a system. So, if heat is extracted from a system, the disorder of molecular motion decreases and hence entropy decreases. So, from this example, you have learnt that entropy is the measure of disorder. If the disorder is more, entropy is more. If the disorder is less, entropy is less. In gas system, the disorder can be increased by supplying heat energy. So, entropy can be increased. Then, in the same gas system, the disorder can be decreased by extracting heat energy. So, entropy can be decreased. This is how the basic concept of entropy can be learnt. Now, you can understand this entropy concept from the PV diagram of three isothermals. Here in this pressure volume diagram, three isothermals I1, I2, I3 at temperatures T1, T2, T3 are considered. These isothermals are interrupted by two adiabatics A1 and A2. Here the adiabatic A1 and A2 interrupts the isothermals at the points A, B, C, D, E and F. This is the point of interception of adiabatic A2 at isothermal I3 at temperature T3. Then this is the point of interception of adiabatic A1 of isothermal I3 at temperature T3. Here in this pressure volume diagram, you can see two cycles A, B, C, D as one cycle and D, C, E, F as another cycle. Here cycle in the sense thermodynamical cycle. So, let us take the cycle A, B, C, D, E. Here in that pressure volume diagram, all along the adiabatic A1 and A2, there is a change in volume and temperature with change in pressure. So, this is the adiabatic A1 and this is adiabatic A2. All along the adiabatic A1 and A2, there is a change in volume and temperature with change in pressure. As I told earlier, you have to imagine two thermodynamical cycles. That two thermodynamical cycles can be Carnot's reversible cycle, A, B, C, D as one cycle. This is A, B, C, D and D, C, E, F as another cycle. Now, first consider the cycle A, B, C, D. In that cycle A, B, C, D, heat energy Q1 is absorbed from A to B at temperature T1. So, this is the heat energy Q1 that is absorbed from A to B at temperature T1. Then the same heat energy is rejected from C to D at temperature T2. So, here C to D heat energy Q2 is rejected at temperature T2. Now, from the theory of Carnot engine, the ratio of heat energy supplied to the temperature of both the cycles is equal. That means, heat energy Q1 is supplied at temperature T1 and heat energy Q2 is extracted at the temperature T2. So, the ratio of heat energy with temperature must be equal according to the theory of Carnot engine. This is the case for first Carnot reversible cycle. This is the case for first Carnot's reversible cycle. Similarly, for the second Carnot reversible cycle DCEF, heat energy Q2 is drawn at temperature T2. The heat energy Q2 is liberated as heat energy Q3 at temperature T3. So, this is the case in the Carnot cycle DCEF. So, according to the theory of Carnot engine, the ratio between heat energy supplied and temperature must be equal. So, Q2 by T2 is equal to Q3 by T3. Then you can equate these two things. So, you will get Q1 by T1 is equal to Q2 by T2, which is equal to Q3 by T3 and to Q1 by T1 is equal to, like that the cycle continues. Finally, you will get a constant. So, in general, going from one adiabatic to the other, heat energy is either absorbed or liberated. This amount of heat energy absorbed or liberated is not constant, but depends upon the temperature. This is what the ratio Q by T says. So, in general, Q is the heat absorbed or rejected at a temperature T. So, Q by T is equal to constant. Applying Carnot's Carnot engine thermodynamic relation, we got Q by T is equal to constant. This constant is called the change in entropy between the states represented by the two adiabatic cycle. So, here we considered two adiabatic cycles A1, two adiabatics A1 and A2. These two adiabatic produced a cycle A, B, C, D and D, C, E, F. In A, B, C, D, Q1 by T1 is equal to Q2 by T2. In D, C, E, F, Q2 by T2 is equal to Q3 by T3. If you imagine more number of cycles like this, we will get Q1 by Q1 by T1 is equal to Q2 by T2 is equal to Q2 by T3 is equal to Q4 by T4. Like that, it will keep on go, we will get a constant. So, in general, it can be reduced as Q by T is equal to constant. Now, let us apply this change in disorder to the entropy. Let S1 and S2 be the entropy for the adiabatic A1 and A2. In the starting itself, I told you entropy means amount of disorder or the measure of amount of disorder. Here S1 is the entropy for the adiabatic A1 and S2 is the entropy for the adiabatic A2. So, the change in entropy S2 minus S1 is equal to Q by T, which is equal to a constant. Here, if the adiabatics are very close to each other, then the heat absorbed Q will be denoted as dQ. So, if the adiabatic is very close to each other, dQ heat absorbed or rejected at temperature T. Therefore, this expression will change to ds is equal to dQ by T. This S2 minus S1 is written as ds, which is equal to dQ by dt. If you convert this into an integral, this expression will change as del S is equal to S2 minus S1, which is equal to integration between S1 and S2 ds is equal to integration between A1 and A2 dQ by T. This is how mathematically the change in entropy can be calculated. So, we started with the definition of entropy, then did some thermodynamic manipulation, then we came to the change in entropy as S2 minus S1, and if the adiabatics are very close, then the heat energy supplied or rejected can be taken as dQ. Then this S2 minus S1 can also be taken as del S. That del S can be calculated by this expression mathematically. The expression del S is equal to integral between A1 A2 dQ by T is a function of the thermodynamic coordinates of a system. So, this function is represented by the symbol S and it is called entropy. So, mathematically this del S is equal to integral between A1 A2 dQ by T is the entropy, and the symbol S is used to denote the symbol S. So, entropy of a function of a system is a function of the thermodynamical coordinates defining the state of the system. State of the system can be denoted by knowing the pressure, temperature, volume or internal energy can be used to know the state of the system, and its change between the two states is equal to the integral of the quantity dq by t between the states along any reversible path joining them. So, here the entropy of a system is related to state of a system, then change between two states is equal to the integral of the quantity dq by t. So, change in entropy is equal to heat added or subtracted from the system over absolute temperature. So, change in entropy is a ratio between heat added or subtracted and absolute temperature. Now, let us come to the unit of entropy. Unit of entropy depends on the unit used for heat energy. You know, heat energy is mostly denoted by joule or kilocalorie. So, the unit of entropy is kilocalorie by Kelvin or joule per Kelvin, kilocalorie per Kelvin or joule per Kelvin. This is how entropy can be understood by in a thermodynamical system and its unit can be learnt. Next, thermodynamical probability. You know, in mathematics the term probability explains the possibility. Possibility for the occurring of an event is called probability in mathematics. In thermodynamics, this probability plays a vital role to understand how many number of molecules or atoms or particles exist in a particular state. So, consider a box divided into k shells, each of area A1, A2, A3, etc. AK. This is that box. The size of the box are not equal. K number of boxes are considered. Now, let us now n balls are thrown into the box in a completely random manner. Here completely random manner means we are not assuring that this many number of balls are going to occupy a particular this many number of balls are going to occupy a particular box. So, that is the meaning of completely random manner. So, let us throw n balls into the box in a completely random manner. Now, observe the distribution of balls into the cells and note it down. Repeat the process for several times. So, after repeating the process for several times, it is observed that certain distribution of balls in certain boxes occur more often than any other. This type of occurrence is called most probable distribution. We are repeating the throwing of n number of balls for several times. Each time we note down how many number of balls occupy each cell. Then if we take a statistics of the balls occupying the cells, a particular cell alone exhibit more number of occupation. This more number of occupation is called most probable distribution. Clearly, the most probable distribution is in which the number of balls in each cell is proportional to the size of the cell. That means a large cell has a greater probability to be hit than a smaller cell. So, smaller cell will get less probability to receive a ball. Larger cell have a large probability to receive a ball. This is the basic understanding in the distribution of balls over the cells. Now, the probability P that the ball be distributed in a certain way among the cells depend on two factors. The first factor is a priori probability, it is denoted as G, or it can also be said as distribution based upon the properties of each cell. Here properties in the sense only area of the cell does an important role, because if the area of the cell is more number of balls can come into contact with that area. So, the first way among the cells is a priori probability G, or distribution based upon the properties of each cell. Then the second one is thermodynamic probability. This thermodynamic probability is denoted by the symbol omega. Now, let us these are the two factors that affect or that controls the way the balls are distributed among the cells. Now, let us take the a priori probability. This a priori probability G I is equal to A suffix I over A. Here this A suffix I is the area of the ith cell. Like that, if there are n number of cells in a box, each cell will have an area. That area can be denoted as A1, A2, A3 like that. Here a general case is given, area of the a priori probability for the ith cell. So, area of the ith cell over total area of the cell. Here this capital A is the total area of the cell. Then if we add the areas of each cell in the box, we will get the total area of the box. That is given mathematically here. A capital A is equal to A1 plus A2 plus A3 plus etc. plus AK. By hypothesis, the sum of the a priori probability all the cells must be equal to 1. That is the basic understanding about the a priori probability. So, summation of the a priori probability is equal to a priori probability for cell 1 plus a priori probability for cell 2, like that it goes. Summation of all these a priori probability is equal to 1. Now, we know that the composite probability is G I to the power n I. This composite probability is nothing but n I balls simultaneously in the ith cell. This is the a priori probability that n I balls simultaneously in the ith cell. Now, the a priori probability of any particular distribution of n balls among the k cells is the product of k probabilities of the form G I to the power n I. This G I to the power n I can be expanded as G I into G1 into G2 into G3 into G4 till Gn. So, that is simplified as G I to the power n I. This G I to the power n I explains the any particular distribution of n balls among the k cells in is the product of k probabilities. Now, this is what G1 to the power n1, G2 to the power n2 etc. and get G I to the power n I etc. G k to the power n k, subject to the condition that total number of the balls is equal to 1. Here the total number of the balls in the sense balls occupied by each cell, sum of balls occupied by each cell, that is given mathematically as n is equal to n1 plus n2 plus n3 etc. nk. The concept of thermodynamic probability is introduced to the system because in the above discussion of a priori probability, all the distribution of balls among the cells are not equally probable. So far we were discussing about the a priori probability. This a priori probability is not sufficient to say that all the distribution of balls among the cells are not equally probable. So, the concept of thermodynamic probability is introduced. In thermodynamic probability, let there be n1 balls in the first cell, n2 balls in the second cell, then n3 balls in the third cell, ni balls in the ith cell and nk balls in the kth cell. These can be number of ways in which the configuration can be obtained. To obtain the configuration of the distribution, there are many ways. This number is called thermodynamic probability for this configuration. Thermodynamic probability for this configuration. This can be mathematically derived as follows. the number of ways n1 balls out of n balls, n1 balls out of n balls distributed may fall in the first cell. So, that can be mathematically written as n c n 1. This is the way you can write the number of distribution of n 1 balls in the total number of balls n. N c n 1 is equal to n factorial over n factorial into n minus n 1 factorial. Then remaining n 2 balls can be distributed in the second cell. These n 2 balls can be distributed in the second cell as n minus n 1 c n 2 is equal to n minus n 1 factorial over n 3 factorial into n minus n 1 minus n 2 factorial. This is the number of ways the remaining n 2 balls can be distributed. Like that you can go till n 3 ball, you can go till n I balls. After n 2 balls, n I balls will come, n 3 balls will come, then n 4, then finally you will get the number of ways the distribution of n I balls. Total number of ways omega is equal to n factorial over n 1 factorial into n minus n 1 factorial into n minus n 1 factorial over n 2 factorial into n minus n 1 minus n 2 factorial. So, the first factor, the first component is the number of ways n 1 balls distributed in the cell. Then the second ball distributed is given by the second factor. Then for the third ball, it will be n minus n 1 minus n 2 over n 3 factorial into n minus n 1 minus n 2 minus n 3 factorial. This is the number of ways the third the n 3 balls fall into the third cell. Into it goes till then n minus n 1 minus n 2 etc. minus n k minus 1 factorial over n k factorial into n minus n 1 minus n 2 etc. n k. So, this is the number of ways the kth cell receives the balls. This can be simplified as follows, which is equal to n factorial over n 1 factorial, n 2 factorial etc. n k factorial. So, this expression represents the thermodynamic probability of the distribution. Then Maxwell-Boltzmann distribution law. This Maxwell-Boltzmann distribution law talks about the distribution of atoms or molecules or particles in a particular energy level. So, in this lecture we have learnt about entropy, thermodynamic probability, Maxwell distribution law. Entropy is a measure of disorder of a system. Entropy, change in entropy can be obtained by finding the ratio between heat added or subtracted to the system and the absolute temperature. Thermodynamic probability is a number of ways n balls distributed in Ni cells, that can be given as n factorial over n1 factorial, n2 factorial, etc. nk factorial. Then Maxwell-Boltzmann distribution law says that Ni is equal to a gi e power minus b beta epsilon I. These are all the concepts we learnt in this lecture. After listening to this lecture, you can answer the following question. Define entropy of a system. What do you mean thermodynamic probability? Define ensemble in thermodynamics. These are the questions you can answer after listening to this lecture. Thank you.